Superconductors. What's a superconductor? A material that can conduct electricity with no resistance. It can carry an electrical current without losing any energy. Superconductors include elements, alloys, compounds, and non-stoichiometric ceramic materials. A material is non-stoichiometric when the numbers of atoms of the elements cannot be expressed as a whole ratio. How do they work? When superconductors are cooled to a specific temperature, they achieve superconductivity. To be more specific, after being cooled, the superconductor's molecular vibrations slow down, allowing the superconductivity. This is an image of a superconductor. Now you may be wondering which part is a superconductor. Well, it is the black circular object on the bottom. This superconductor is demonstrating the Meissner effect that will be explained later in the video. To fully understand superconductors, you must understand superconductivity, the principle behind superconductors. The definition is the absence of resistance in a conducting material, allowing a continuously flowing electric current. Each superconductor achieves superconductivity at a critical. In this picture, the magnet can float due to the superconductivity of the superconductor and the Meissner effect. There are three types of superconductors. 1. The type 1 or soft superconductor. 2. The type 2 or hard superconductor. And 3. The high temperature superconductor. Type 1 or soft superconductors show some conductivity at room temperature. Generally, they are metals or metalloids. They need an extremely low temperature to slow down their molecular vibrations to allow a continuously flowing electric current. The BCS theory describes that electrons pair into Cooper pairs through interaction with the crystal lattice of the superconductor, resulting in an attraction between the electrons and the lattice vibrations. Type 2 superconductors also need a very low temperature in order to achieve a continuously flowing electric current. The transition from the normal state is considered to be a slow change. As the temperature decreases from the critical temperature, the superconducting properties increase. High-temperature superconductors were more recently found, discovered by Alex Mullen and J. George Bednorz from Switzerland. In 1986, they found a non-stoichiometric ceramic material that had superconductive properties. The material they found was a non-stoichiometric oxide of lanthanum, barium, and copper. It had a record-high critical temperature of 35 degrees Kelvin, and if slightly modified, the material could have a high critical temperature of 50 degrees Kelvin. Another non-stoichiometric ceramic material that was found was yttrium barium copper oxide. It attained superconductivity when cooled with liquid nitrogen that had a boiling point of 77 degrees Kelvin. To put into context, it was a temperature of negative 369 degrees Fahrenheit. Compared to type 1 and type 2 superconductors, 35 through 50 degrees Kelvin is a very high critical temperature, hence why it is called a high-temperature superconductor. The definition of the Meissner effect is a repulsion of the magnetic field from the interior of a superconductor below its critical temperature. As seen in the first image, the floating of the magnet is due to the Meissner effect, because the superconductor repels the magnet. Applications. Superconducting materials can be applied to superconducting magnets without iron cores, which are used in particle accelerators, nuclear magnetic resonance instruments, levitating trains, and even magnetic refrigerators. Applications side note. Most applications that use superconductors use type 1 or type 2 superconductors since they were discovered first, and they can also be molded into strong, flexible forms.
Created using Powtoon.